Hello students and welcome back. On today's video, I'd like us to focus on autonomous first order differential equation. So what is that by definition? It's an equation which the independent variable does not appear explicitly. So that is to say, if we have dy by dx equals a function of only y, where x does not appear at all, okay? Since we know that our y here is the dependent and x is the independent. So that is to say, a function that does not contain x at all. Let me just give you guys an example. We're gonna have something like dy by dx equals can say y squared minus y, like that. So this is an autonomous first order differential equation. X does not appear anywhere, okay? However, if you have something like dy by dx equals half xy, can we still consider this as an autonomous differential equation? No, we cannot, because our independent variable is appearing right there, isn't it? Yes. So now let's see what else can we know about autonomous differential equation. So if we said from this example, let's suppose if we set y squared minus y to be equal to 0, then we're gonna find that y into y minus 1 equals 0, then y is 0, or y equals 1. Now if we set our autonomous differential equation to be 0, we find what we call critical points. So every time when you're dealing with an autonomous differential equation, you set it to 0 to find your critical points. Now, what is the purpose of those critical points? We're going to use the critical points to draw our phase line and solution curve. Okay, so there are a few things that we have to keep in mind. Remember that if our derivative is greater than 0, it implies that derivatives greater than 0 means positive. It implies that our function is increasing, isn't it? And also keeping in mind that if it is negative, that means it's less than 0, then it is decreasing. Okay, so if our derivative is greater than 0, you have an increasing function. If it's less than 0, we have a decreasing function, just like that. So now for the phase line, if we have the same cases, I'm just rewriting the same thing again. This case where our function is increasing, then we're gonna have arrow. We're gonna have our arrow facing up. Okay, don't worry, I'll show you guys what a phase line looks like, so just bear with me when I just give you all these notes, few tips. So if it is a decreasing function, then we're gonna have our arrow facing down. So what I mean by all this information that I put up here, we can use an example to break it down quickly. Since we found this as our critical points, I'll just use this as an example again. We have found our critical points to be 0 and 1. So on the phase line, we include our critical points. Let me just draw it like this. This is gonna be my phase line. Okay, so I see that I have 0. I can put it here. That's 0 there. Then I also have 1, like that. Okay, so yeah, this is phase line. Okay, so on my phase line, I said that if the derivative is increasing, is greater than 0, is positive, we have an arrow facing up. Or if it's negative, we have an arrow facing down. Okay, how are we gonna find where is our function increasing and decreasing? It's still the same way that we used to do in calculus. We want let's see, in our function, if we substitute back in our function any number less than 0, any negative number. Okay, if I plug any negative number in here, it will um always be positive. However, this side is gonna be negative by negative, it's positive. Okay, that means it is increasing, and if it's increasing, we know dy by dx is greater than 0. Increasing, dy by dx greater than 0, and we know for the phase line that means our arrow has to face up. Okay, so for anything less than 0, arrow faces up like this. And in between 0 and 1, I can take half square, it will remain positive, then we have a negative right there. That means we're gonna have an arrow facing down. If we have negative, our dy by dx is less than 0, decreasing. When dy by dx is less than 0, we have arrow down, isn't it? So our arrow here is gonna face down like that. And for anything greater than 1, let's put 2. 2 square is 4. 4 minus 2, then we have a positive number. And if it's positive, then we know it's increasing. And for the phase line, we have an arrow up. Like that. So just like this, for the example, I'm done with drawing the phase line. What is left of is to draw a solution curve. Okay. With this phase line now, it's easy for you to draw a solution curve on the side here. Okay, you do not have to worry about anything. This is just easy. If you feel like I have lost you in between, feel free to rewind the video so you can understand what we are actually trying to do here. I will do more example so you guys can follow up. So now, drawing the solution curve on the side, I can construct from 0 like that with dotted lines, and also from 1 I can construct like that. Yeah, so this is gonna be now my solution curve that I'm gonna draw here. I already know that here at the bottom we are having an increasing function. So for increasing function, I want my slope to be positive. So I can roughly draw a graph that goes like that. Yeah, goes like that. So the slope is always positive. However, between 0 and 1, we have a negative gradient. So a slope like this is suitable for our negative gradient, isn't it? Then for anything greater than 1, we see that it's an arrow facing up, then that means we want another increasing function again. So I can just draw it like that. Yeah, just like that. It's not a straight line, it's a curve. Just like that. Okay, so this is the solution curve. Okay, so once you got your phase line correct, knowing where the arrow is facing up and down in between the critical points, then your solution curve is just gonna be a piece of cake. It's just gonna be too easy for you to go about it. Okay, so now there are a few more things that I have to outline now from our solution curve. If we look at our curve on the critical point, let me just remind you guys what is here. Here we have a critical point 0, and here we have our critical point 1. Okay, since the camera cannot show that side. I'll just write the critical points there. So what is happening on the critical point 0 here, when we are looking at our solution curves, we see that the solution curves are coming closer and closer to our critical point 0. Okay, so that means in this example, 0 is an attractor. So we see that they're coming together. It implies we are having an attractor. So the curves are attracting each other. We have an attractor at y equals 0. Okay. However, if we look at the other critical point 1, what is going on there is that we see the other solution curve is going away like that, and also this one is going away like that. They are not coming closer to 1, isn't it? So for this critical point right there, we're having what we call a repeller. Yeah, it's a repeller like this. A repeller at y equals 1. Okay, so now we're done with our solution curve and interpretation of everything. At 1 we have a repeller, and at 0 we have an attractor. So let's look at another example so you guys can get what is actually going on. I hope you will feel free to pause the video and try the example yourself before I do the solution. So another example, we have dy by dx is equal to y squared minus y to the third. So we can just quickly rewrite it as dy by dx is the same as, if we factor out y, then we remain with, or let's just factor out y squared, then we remain with 1 minus y, like that. So to find our critical points, we have y squared 1 minus y set equal to 0. Then we know that y is 0 and y is 1. It's a coincidence that we are getting the same critical points again. However, let's see where this is gonna take us. So now the first thing that we want to do is to draw our face line. Okay, so on our face line we have 0. Let me put it here. Then we have 1, like that. So what we want to know is, where is our function increasing? Where is our derivative greater than 0 and where is it less than 0? Okay, so for anything below 0, let's take -1. Okay, so we see that since we rewrote our derivative like this, and now we are choosing anything less than 0, here it's always going to be positive, isn't it? So we are just worried about here. So negative times negative, let's choose, if we chose -1, then it's going to be negative times -1, then that becomes positive, then everything is positive. And we already know that if we are having our derivative to be positive, we are having an arrow facing up. Our arrow is going to face up like that. Okay, so now between 0 and 1, I can choose half. Yes, so 1 minus half, that is still gonna be positive. So my arrow again is facing up. And for anything greater than 1, I can choose 2. 1 minus 2, that is negative. Since this is always gonna be positive, then my arrow is gonna face down. We get that dy by dx is less than 0. Okay, it's negative. Yeah, so that is gonna be my face line. This is not part of our arrows, it's just an axis. So that is the face line. Now we can quickly draw the solution curve and see which of our critical point is a repeller and which is an attractor. So quickly, we know that with these arrows, now we can just quickly draw our solution curve. If the arrow is facing up, we know gradient is positive. Then we need a positive gradient like that. And similarly, for this case, our arrow, we see that it's facing up. That means we want an increasing function. We can then again have a solution curve like this. Okay, so now for anything greater than 1, we're going to have a negative gradient since our arrow is facing downwards. So we're going to have something like this. So this is our solution curve. Now again, looking at the first critical point 1, we see that these two curves are coming together. So here we're going to have again an attractor. We have an attractor at y equals 1. However, at 0, the functions are not coming both together. They're not coming together to 0. So that means here we have a repeller. I hope now it's clear what we are doing. So I'll give you guys another example that you should feel free to try on your own. dy by dx equals ln of y plus 2 to the power y. Okay, go ahead and try this example and see if ever you understand what is going on. Thank you so much guys for watching. I appreciate the support and I hope you find these videos helpful.